And we are good whenever you're good.
Okay. Let's do it. Alright, so I'm giving this talk on category theory because I'm running a seminar this term on class field theory, and the fateful moment has come when we have to talk about group cohomology. And group cohomology is something that doesn't make sense at all if you're not familiar with this language. So first I want to tell you what category theory is before I actually tell you category theory itself. So what it is it's a language for reasoning, both in mathematics and computer science and logic and many other areas. You can't expect to solve very substantial problems with category theory. It's more of just a kind of unifying framework that can allow you to organize the way you think about mathematical concepts. But the advantage of category theory is that it will save you from wasting time bashing out things that are essentially just formal consequences of the abstract structure that's present. Okay, so maybe I'll just tell you what a category is. So here's a definition. A category has three things. Okay, so a category C consists of three pieces of information. So there's a collection of objects. So you have this collection, and its elements we call objects. Okay, so there's a collection of objects, ob C. And for any two objects, C and C prime, C and C prime in this collection of objects of the category, you have a collection, let's say Hom C, C prime. Okay? So the way you want to think about a category is it's like a kind of universe where certain kinds of mathematical creatures live. So you can think about a category whose objects are sets, and for any two sets, you let Hom C, C prime be the set of functions from C to C prime. You can think of a category whose objects are groups or rings or topological spaces, smooth manifolds, and in each one of those cases you have some appropriate notion of morphism between those objects. Okay, so the elements of this collection, Hom C, C prime, we call morphisms or arrows. Okay, and if I have a function, if I have a morphism f from C to C prime, then I'll often denote it like this. I'll write C, and I'll just draw an arrow and label that arrow f from C to C prime. Okay, so there's these two pieces of information, and lastly, and most importantly, we have something that ties them together. So we can compose morphisms whose domains and codomains match up properly. So there is a composition and it, of course, motivated by all of mathematics, we write this composition as a circle, and what it does is it takes, so I hope it's clear what I mean by this, but it takes a morphism from C to C prime and a morphism from C prime to C prime prime, and it produces a morphism from C to C prime prime. Okay? So at this point I should mention, as I mentioned before, a lot of examples of categories that we are interested in are categories of certain kinds of sets equipped with certain kinds of functions. Now, if I look at the category of all sets, then this collection, the thing I'm calling a collection, will not be a set because there's no set of all sets. Okay? And but between any two sets, the set of all functions is a set. Okay? So you have this kind of weird foundational issue that you may be talking about things that are like sets, but they're too big to actually be sets. But we're just going to ignore all those issues. Okay? So there's this composition operation, and I mean it's not just some arbitrary map. It satisfies some important properties. So the first property is that, so I should really say for C, C prime, C prime prime objects of this category C, okay, we have this composition like this. And what it satisfies is, first of all, for every C, for every object C of C, there is a very special morphism. And that morphism is the identity, also denoted id C. Okay, and this thing lives inside Hom C C. Okay, so on every object you have this kind of identity map, identity morphism, and it behaves as an identity for this composition law. So i.e., if I have C and I draw the identity map here, 1C, then whenever I have any map from C prime into C, okay, F, any morphism from C prime to C, if I do F and then I do 1C, that's the same as just having done F, okay? And symmetrically, whenever I have any map G from C to some object C double prime, if I do 1C and then G, that's the same as just having done G, okay? So this kind of parallelogram commutes. So I'll write that in equations. What I mean is F equals 1C circle F for the first triangle, okay? And then for the other triangle, I mean G equals G circle 1C. Okay, so it behaves as you would expect. It's an identity morphism. And secondly, composition is associative. Okay, i.e., whenever this makes sense, I need that F circle G circle H equals F circle G circle H. And this means that I can write down products, okay? I can compose however many morphisms I want, and I don't have to write brackets. There's no ambiguity. Okay, so that's what a category is. So what are some examples of categories? Well, now is a part of the talk where I pretty much just list every kind of mathematical object I know to you. So sets, rings, groups, smooth manifolds, topological spaces. I'll stop eventually, I promise. C-star algebras, schemes. I mean, I could keep going all day, right? And you can really restrict attention, so I could take, torsion-free abelian groups. So modules over some ring, so I should write in red the kind of aristocrats of the society. So abelian groups form a very nice category. Modules over some ring R, for R a ring. Alright, so notice that if I take R to be the integral group ring of a group G, then I get the category of so-called G modules that was mentioned last week. Okay? So you can take any of these objects, these will all form categories, and of course, in each one of these cases, there's an appropriate notion of morphism, structure-preserving transformation, okay? So for sets, it's functions. You've got ring homomorphisms, group homomorphisms, smooth maps, continuous functions. Well, there's a few choices here. Morphisms of schemes, group homomorphisms, module homomorphisms. It's all the same kind of idea, right? So those are some examples of categories that come up a lot. And as I said, these ones in red are actually very nice because they form what are called abelian categories. And abelian categories are where you can do homological algebra. So you can talk about kernels, images, co-kernels, exact sequences. All these concepts make perfect sense in abelian categories. And that's very important for, well, homological methods, such as group cohomology. Okay, so there are some examples. Now, I can also just construct categories, toy categories. I can just, given any set, I can consider a category that has the elements of that set as its collection of objects. And of course, I'm forced to put an identity arrow on all these elements, okay, so, or I guess I denoted it by 1, right? So I just take an object for each thing in my set and stick an identity arrow on it, and that's a perfectly valid category. So these are called discrete categories. So that's just to illustrate to you that a category does not have to arise, it doesn't have to have any intrinsic meaning. It's just a formal structure that satisfies some properties, okay? So now I want to define a few fundamental notions that have to do with categories. So we'll talk about transformations between categories momentarily, but before I do that, I want to define some very basic notions. So here's the definition. Let's see, so okay, C, let's just say at the outset, C and D are categories. Okay, so definition, an object, so let me call it U, or yeah, let me call it U. So if I have an object U in a category C, then I call it initial. When given any other object of that category, U emits a unique morphism to the prescribed object. Okay, so U, if you give me any other C in the category, then I can find a unique morphism. So there exists a unique morphism from U to C in the category if given any C in a collection of objects of this category, there exists a unique morphism. So I should just write a unique, let me call it F. There is a unique F in the morphism set on C, U, C. Okay, so this is a very intuitive notion. So what are some examples of initial objects? Anybody have any ideas? So what if we look at the category of rings, right? Say commutative rings. What's an initial object in the category of commutative rings? Well, I can just take the integers, right? The ring of integers. I have to send 1 to 1, so I have a unique ring homomorphism to any other ring. Okay. So dually, we call that object U in C terminal if given any object C of C, there's a unique morphism from that thing to that object. Okay, so this would just be reversed. Okay, so that's very useful. And now I'll talk about monomorphisms and epimorphisms. So as I mentioned before, the morphisms of a category, if you look at this definition, there's nothing that tells you that the morphisms of a category actually have to represent functions, okay? And there's nothing that tells you this composition is composition of functions or anything. So, unfortunately, the concept of injectivity and surjectivity no longer makes sense for general categories. So here are the substitutes, okay? So recall F is injective if whenever you have two points in the domain that give you the same value, they must be the same point. Okay, so that's what it means for a function between sets to be injective. And now here's the categorical substitute for injectivity. A morphism F from C to C prime, okay, these are objects in my category C, is mono if basically the same condition holds, but now I can't talk about elements. I can't talk about elements of C anymore. So I have to replace it with something. So if for every morphism, or I should say morphisms, let's say phi and psi, from some other object, C prime prime, into C, okay, we have that F circle phi equals F circle psi implies that those two are the same ones. Okay, so you can see how this is generalizing injectivity. Just think about this phi as your x and this psi as your y, okay? And in many cases, you can actually make this rigorous. So suppose we're in the category of topological spaces, right? And suppose you give me a a morphism that's mono, then I can pick C prime prime to be the one-point topological space, right? And I can pick phi to just take that point and stick it in x, and psi to take that point and stick it at y. And then you see that it has to be an injective function, okay? So in the category of topological spaces, monos are injective, but you should maybe think about whether all injective functions are mono. Okay, so then dually we define epimorphisms. So f from C to C prime is epi. So what do I want to say here? If for every morphism, so you can see that the concept of being mono is equivalent to being left cancellable, okay? So for epimorphisms, it's going to be right cancellability. So for every morphisms, phi and psi, I'll decide this later, we have, well, I want phi circle f to be equal to psi circle f to imply phi equals psi. So these are the analogs of surjective maps, the categorical analogs of surjective maps. So when does this make sense? Well, I need these to have codomain C prime this time, right? And they're going to some other C prime prime. Okay. So whenever I have these maps that are coming out of the codomain of F, going like this, and the composite from C to C prime prime agrees, then it must follow that those are the same map. Okay. So there are some instances where this behaves a little bizarrely. For example, in the category of rings, if you look at the unique morphism from Z to Q, okay, the ring of rational numbers, it's actually an epimorphism. Why is that an epimorphism? Well, if you have two functions that are defined on the rationals, okay, and you know that they agree on the integers, then basically just by some easy algebraic manipulation, you can show that they, in fact, must be the same map on the rationals. Okay? So that's why the map from Z to Q is an epimorphism in ring. Okay, so finally, there's this property that's very important. The definition of morphism F from C to C prime. Again, these are objects in my category fancy C, is iso if there exists a morphism G from C prime back to C, such that when I use this composition operation afforded to me by the category, I have F circle G. Well, first I do G, then I do F, so I go, then I come back. That needs to be the identity on C prime, and G circle F needs to be the identity on C. Okay. So if I can find a morphism such that, you know, it's kind of acting as an inverse relative to this composition, then I call this thing an iso. Okay. Also invertible. I may use that word too sometimes. Okay. So this is all kind of dry so far. It's just stuff you already know from doing enough math. But now we're going to talk about transformations between categories. So when you introduce groups, of course, you don't want to just look at functions between groups because that's completely ignoring all the structure that you have. Okay. Same thing with categories. We're going to talk about morphisms between some kind of correspondences, transformations between categories that preserve their structure. Those transformations are called functors. Okay. So what is a functor? Again, C and D are categories. There are two kinds of functor. Okay. So here's the definition. So a covariant functor. A covariant functor F from this category to this category. Well, what data do we have in a category? We have a collection of objects and we have a collection of morphisms. We want to preserve the structure. So a covariant functor it has a behavior on objects, okay, so it associates to each object of the domain category, so to each little c in the collection of objects of the domain category, an object denoted fc in the codomain category, okay, and it also has a behavior on morphisms. So to each morphism, so I'll write f in Pom C, C, C prime, it's going to give me a morphism in the codomain category between the images, okay? So I'm going to denote that by FF. So it's going to give me an FF in D, FC, FC prime. Okay? So again, every object in C, it gives you an object FC in D. And whenever you have an arrow between two objects over here, you take the images of those two objects, it gives you an arrow between those images. Okay? And it has to be coherent in the sense that it respects the composition laws on both categories. So in other words, f of a composition is the composition of the behaviors on the individual things, and, of course, it needs to take the identity arrow on every object C of C to the identity arrow on the image object in D. Okay? So that's the concept of a functor. It's pretty intuitive. And these things are everywhere in math. So category theory originated in algebraic topology. And in algebraic topology, their problem was that they were trying to classify certain different kinds of topological spaces. Now, if I give you two topological spaces, it's very difficult to prove a theorem of the form there exists no homeomorphism from x to y directly. Okay, it's very difficult to write down a proof that no matter how clever I am, I will never come up with a homeomorphism between x and y. However, if I can attach in algebraic invariants to x and y, and I can compute those invariants, and then I can calculate that they don't agree, okay, then it must follow that x and y cannot be homeomorphic. So the idea is that if you have a topological space, you associate to it some kind of algebraic object, such that whenever two topological spaces are homeomorphic, the associated algebraic objects are isomorphic. Okay? And then if you're trying to distinguish two topological spaces, you need only compute enough invariants until you find a place where they disagree. And unfortunately, you can calculate many, many, many invariants, and they may always agree, but at the end of the day, they may still turn out to not be homeomorphic. Okay, so somehow this test can never guarantee that they are homeomorphic. Okay. Usually we don't have invariants that are that fine. Okay. So that's where all these ideas originated from, and of course, when they came up with these invariants, sometimes two different people would come up with their own little versions of some invariant, and then they'd realize that whenever they calculated this thing on topological spaces, they always got the same result. So they'd say, wait a minute, maybe these invariants are really the same in some sense. So to tie this with the situation here, a topological invariant would be a functor from the category of topological spaces over to, say, the category of abelian groups, right? And then and the next thing that I want to talk about after I give some examples are these things called natural transformations, okay? And natural transformations are going to be the transformations between functors. In other words, it's the way that we can formalize what it means for two topological invariants to be exactly the same. Okay, so before I go there, let me just give some examples of functors. So you can probably give a lot of these. So if R is a ring, we can take its group of invertible elements. Okay, so R cross will be a group. Say it's yeah, well, I don't need it to be commutative. So if I was a commutative ring, more generally, what I can do is I can take a group of n by n invertible matrices with entries in R. Okay, so GLNR, this is a group, right? And there are many constructions from linear algebra. So if V is a vector space, then V star, in other words, the vector space of linear maps. So say it's a vector space over a field K, then the vector space of linear maps from V to K gives you another vector space, right? And what's more, okay, in all of these examples, whenever you have some kind of morphism between two rings, you get morphisms between their group of units, you get morphisms between these GLNRs, okay? So if I have a morphism from R to S, then I will get a morphism from GLNR to GLNS just by including the entries into S, right? By using that whole morphism. And similarly, if I have a linear map between two vector spaces, okay, so notice that if T goes from V to W, we get a linear map between their dual spaces. But there's a bit of a kink here, because the way it works is, so let me draw a picture. The way it works is V star is the space of all linear functionals, okay? In other words, linear maps from V to the underlying field. Okay. Now, say here's my field, right? If I have a functional on W, so say here's a phi, this phi is living in W star, right? Then I can get a functional on V. Okay, I have this T that's hanging around here. I can get a functional on V just by following T and then following phi. So here's phi circle T. Okay? So this is hinting at a general phenomenon that I'll talk about after this, but somehow we can pull back functionals along a linear map. We can't push them forward, okay? So the way it behaves is it takes phi and it sends it to phi circle T. Okay. So again, you see this kind of behavior. For every object of some category, namely the vector spaces, we get an object of some other category, also the vector spaces. For every linear map between two vector spaces, I get a linear map between their dual spaces. But here, I was talking about covariant functors, whereas here, it's flipping the direction, okay? So this is an example of what's called a contravariant functor. So to get the concept of a contravariant functor, it still sends every object to some object, but now, if I have a morphism from C to C prime, that's not going to go to a morphism from FC to FC prime. It'll go the other way. So I would take this prime and stick it over there. And then of course I have to fix this composition law, right? It'll be f of f circle g equals f of g circle f of f. So everything flips. So contravariant functors are also called presheets due to reasons from algebraic geometry that I won't go into. But just in case you see that word, you don't know what it means. Okay. So those are some examples of some functors, right? And now I want to talk about an extremely important example of functor that comes with almost any category. So when I define a category, I said that its collection of objects it just had a collection of objects, and between any two objects you had a collection of morphisms. Now, if it turns out that whenever I pick two objects, the collection of morphisms between them is actually a set, okay, so it's not too big to fail to be a set, then we call that category locally small. Now, if you look at the examples of categories I gave, they're all locally small, okay, there's nothing bad happening here. So if I have a locally small category, then I get two very natural functors out of it, and they work like this. So these are called the Hom functors. Okay, and these functors go from the category to the category of sets. So we define, again, C is a category. If I fix any object for C in ob C, okay, I define this functor hom c, c dash, okay? And what this thing does is it eats an object c prime of c, and it returns to you the set of morphisms in C, between C and C prime, okay? So, as follows. So, I should write down its signature. It's a functor from this category to the category of sets. I think I'm just going to write this just in Roman text, okay? So, this category, and this is the category of sets with functions, okay? So the way it works is on objects, it takes an object C, C prime of C, and it maps that to hom C, C, C prime, okay? Now, think about how it might act on morphisms. If I have a morphism from, say, C prime to C prime prime in my category, how do I get a function from hom C, C, C prime to hom C, C, C prime prime? So, whenever I have this situation happening in the domain category C, this gets sent to, this is a lot of writing, maybe more than is necessary. Okay, so I want to send it to an arrow between these two sets. And what am I going to do? It's going to be denoted F lower star, okay, where F lower star is the push forward map. Okay, so it takes a morphism from C to C prime, and then it post-composes it with this. Okay, and then you get a morphism from C to C double prime. Okay, so F lower star of phi equals F circle phi for phi in this set. Okay. So that's what happens when I fix the first argument of the hom, okay? But I can also fix the second argument. So let me just see. So we also define for C in C, another functor, and this one is a contravariant functor. So notice over there, the direction of the arrows was preserved. Now it's going to be reversed. So this guy eats an object C prime of our category and returns the set of all morphisms between C prime, from C prime to C, okay? So this goes from our category to the category of sets. And how does it behave on objects? Well, it takes a C prime here, and it spits out C prime C. Okay, and how does it behave on morphisms? Well, let's say I have a morphism F from C prime prime, from C prime to C prime prime in our category C. I don't have space for this. So what it's going to do is it's going to send this over to the pullback along F. Okay, so here I have, so where am I going? I'm going from C prime to C here. And now the arrow is going to be the other way. Okay, so how do I define this map? This is F upper star, okay, where F upper star is the pullback. So if I take a phi that's over here, so it's a morphism from C prime prime to C, then I precompose it by this F, and then I get a morphism from C prime to C. So this is phi circle F. This is for all phi in C. Where is it? It's in C prime prime C. Right? So that's great. And the reason these functors are so important is, I may have time to talk about it later, there's this thing called the Yoneda lemma, which somehow tells you that if you understand this functor, okay, so suppose you have an object C in your category. If you can understand this functor, or that functor, whichever, so if you can understand the Hom functor that's associated to C completely, then in some sense you understand the object itself, okay? So if you understand how it's interacting with all the other objects in the category, that determines what the object is. Now that's a very rough statement. I'll make it a bit more precise later. But it's very useful, and it underlies many ideas in modern algebraic geometry, so it's very important. Okay, so of course there's another functor you may have heard of if you've studied rings. Okay, so if let's say A is a commutative ring, sorry, I should say if R is a commutative ring and A is a module over R, okay, so if you've never heard of modules over rings, basically it's just like a vector space, but instead of having a field of scalars, you have a ring of scalars, okay? So since you've replaced the field with a ring, linear algebra doesn't really work properly anymore. It's much uglier. But anyway, these are of a lot of interest. So if you have a module over R, we get a functor. We get a functor, and what is it? It's just a tensor over R with whatever, and that eats R modules, and it produces new R modules. So it takes an R module B, and it produces the tensor product of A and B, okay? And what it does is it'll take a map, a module homomorphism from B to B prime F, and it will produce the map. So here you have A tensor over R with B, and then it'll produce id tensor F to A tensor over R with B prime. Okay, so if you fix any module over R, you get this thing that eats another module over R and produces a tensor product with A. Okay, now somehow this functor tensor is very related to these Hom functors. Okay, so let me just maybe give some more familiar examples. I don't think many people are comfortable with this. But so if G is a group, so I'm still just giving examples of functors. If G is a group, okay, we can view G as a category. Okay, even if G is a monoid, if you have a set with an associative binary operation for which there exists an identity element, that is to say a monoid, then I can form a category in a very easy way. And the way I do it is I draw a dot. Okay, and this dot is going to be the only object in my category. And for every element of G, okay, I know that I have an identity for G, so I'll call that E. Now for every element G of G, I draw an arrow from this dot to itself, okay? And now I define the composition law in this one object category to just be multiplication in G, okay? Now you'll see that this works exactly, and in fact, any group corresponds to a locally small category where with one object where every morphism is invertible. More generally, a monoid corresponds to a locally small category with one object, period, okay? So you can view any group as a category, and then it's natural to ask, what is a functor from G viewed as a category to the category of all sets? So if you think about what the definition of a functor is, it says, for every object in here, okay, well there's only one of them, I gotta get an object of this category of sets, right? So it takes this dot, and it sends it to some set, call it x. And it takes all these arrows that are going from this dot to itself, and it sends all those arrows to functions from x to x. Now, since these are all invertible, and functors preserve the compositional law of a category, it follows that all these arrows on the set x are invertible. Okay, so here's you know, G, this is the category G, and then over here, we have the category of all sets. And there's all these sets in here, but we're only going to draw one of them because this functor only picks out one set. And it sends all of these arrows, okay, the identity has to go to the identity on X. And then you get all these arrows corresponding to group elements. Okay, so this is, what is it? It's a group action, right? Because it's giving you, for every element of your group, a bijection from X to X. So this is a group action. This is nothing more. So it's a set equipped with an action by G. And people call these G sets. Okay? Now, one of the things that's done in representation theory, maybe I'll just draw this line all over again. One of the things that's done in representation theory is that group actions are great, right? I mean, it's nice, but there's not a lot of data that you can attach to a group action. I can really just think about things like how many points does each one of these elements fix, blah, 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 things like that, right? But now I'll ask this question. What is a functor from G into, say, the category of complex vector spaces, or even finite dimensional, the category of finite dimensional complex vector spaces. So maybe I'll just write fit. So what these are, what does it do? Let's unwrap the definition again. For every object of this category, it's going to pick out a vector space over the complex numbers. And for every element of your group, in other words, the morphisms, the self-morphisms of this unique object, it's going to pick out a linear bijection of that vector space. Okay? So these are called representations. So a functor like this is nothing more than a finite dimensional complex representation of G. Now, you may ask, so what? I mean, why is a representation any better than a group action? The thing is that if G is acting on a vector space via linear transformations, then all of a sudden, you can look at a group element, you can look at the linear transformation by which it's acting on this space V, and you can say, what's the trace? What's the determinant? What's the characteristic polynomial? You get all this algebraic data attached to the elements of G. So in some sense, okay, this is very abstract, but to be more simple-minded, what I'm really doing is I'm just assigning an n by n invertible matrix to every element of G, okay, over the complex numbers. So I'm viewing G in some sense as a group of matrices. Now, I could be crushing down a lot of structure, right? So, for example, I can take all of these self maps on this dot and send them all to the identity map on the vector space. That's a very stupid representation. It's not very interesting. But the point is that if G is finite, okay, or more generally, if G is a compact Lie group, every finite dimensional complex representation will break up into a kind of decomposition of what are called irreducible representations, okay? And if you look at the collection of irreducible representations, up to equivalence, there's only finitely many of them. So this is a thing you can ask now. Given any group, I can ask, write down a list, a complete list of representatives for the isomorphism classes of its irreducible complex representations, okay? And another thing I can do is I can just start writing down the traces, okay? I can make a table where this way I write all of the irreducible representations of G, And then over here I write, say, the elements of G. And then I can, in this spot, I can write the trace of the linear transformation attached to that element on that particular vector space. And I get this table of numbers. That's called the character table of G. Okay? So for more information, PMath 735. So that's another great example of a functor. It's just a representation in Cassim in this framework. Okay, so finally, I want to talk about natural transformations. Okay, so you've probably heard the word natural in a mathematical context before. So if you've taken a course in linear algebra, you'll see that they claim that every vector space is naturally isomorphic to its double dual. Okay, whereas they're not naturally isomorphic to their single duals. You have to do it twice to get it to come back, right? And that's kind of not that surprising when you think about it. When you take dual spaces, the arrows flip, and then once you take it again, they go back, right? So you kind of don't have a chance to get this if it's going the wrong way, right? So that's the next example I want to talk about. But that won't make any sense unless I define what a natural transformation is. Okay, so I need to make sense of a transformation between functors. Okay, now functors are already transformations between categories. So this is getting kind of abstract at this point. But the point is that if I want to make precise what I mean by every vector space is naturally isomorphic to its double dual, I'm not really making a statement about vector spaces. Okay. I'm making a statement about functors. And the functors in question, there are two of them. One of them is the identity functor on the category of vector spaces. Takes every vector space, gives you itself. Takes every linear map, doesn't do anything to it. Leaves it alone, right? The other functor is the one that takes every vector space to its double dual space, and every linear map to the dual of that map, okay? So we have two functors from the category of vector spaces to itself. And when people say that a vector space is naturally isomorphic to its double dual, what they really mean is that these two functors, the identity functor and the double dual functor, are naturally isomorphic to one another. Okay? So what does that even mean? Again, I have two categories C and D. So suppose F and G, these things are functors from C to D. Okay? So these are functors. I need to talk about what a natural transformation from F to G is. A natural transformation, eta, from this functor, and I put a dot here just to kind of remind you that this is encoding a whole ton of information inside of it. Well, what is it? What this eta is going to do, okay, you can think of F as taking all the objects of C and kind of painting this shadow of C and D, right? Same thing with G. What eta is going to do is drag the picture that F paints in D onto the picture that G paints in D in such a way that it's coherent with all the data present in the category, okay? So what I need is, for each object C of the domain category, I need a component of eta. So a morphism, which I'll denote eta sub C, and it's going to take FC, okay, the image of this object under the first functor, to the image of that object under the second functor. Okay? It goes from FC to GC. Now I'm not done, because this would be very silly if I was done, because, I mean, as it currently stands, I haven't said anything about kind of coherence between this big family of morphisms I've given you. So that's the next piece of the definition. So for every object of a domain, it gives me this thing that goes between the images of that object under these two functors in the codomain category, such that for all morphisms, so I should say a morphism like this of D, okay, in case that wasn't clear from context. such that for all morphisms little f from C to C prime, the following square commutes. So in other words, no matter which path you take through this square, your fate will be the same. Okay, so here is the image of this little f under the first functor, and now I draw a similar picture for the functor g. Okay, and now how do I form the square? I just put in the components. So eta c, eta c prime. Okay. So I know that this may seem very unmotivated at this point, but the next few examples should convince you that this is actually the right thing to do. Okay. Okay, so let's do an example right off the bat to make this make a bit more sense. So let the domain be a group viewed as a category as before, and let codomain again be set. Then f and g are simply g sets. Okay, so say f takes this dot to some set x, g takes this dot to some set y. Okay? Now let's think about what a natural transformation between f and g, okay, these two group actions, might be. Actually, for simplicity, let's just take them to be the same object. Okay? So you have a group which is acting on in potentially two different ways on the same set. What does it mean to have a natural transformation between f and g? Then a natural transformation, eta, from f to g, what does it do? Let's look at the definition. For each c in the domain of C, okay, that is for each object of this category, oh, there's only one object because it's a group, okay. I get, so this gives us a component, so a morphism, a function really, right, gives us a function, eta dot, from f of dot, which is x, to g of dot, which is x. Okay, it gives us a function like this, such that, and now what does this coherence condition amount to? Well, I want for all morphisms f from between these two objects in G, okay, but wait, what are the morphisms between dot and dot in G? Those are precisely the group elements, right? So this amounts to saying, for all the elements of my group, what do I need? So this is x, right? F dot is x, and f dot is also x. And then over here, these are both x too. And then my components are the same. They're both eta dot. And now what are these vertical maps? Well, fg, okay, fg is how g acts on this set x. So it's the bijection of x that's associated to this group element by f, okay? So I'll write it like this. And then over there, you have the one associated to g from capital G, right? So what this is telling you is that you have this function from the set to itself such that if I take an element, I send it through the function, and then I let g act on it after that. That's the same thing as first having let g act on it and then send it through the function, okay? So a natural transformation is giving you nothing else than a function from x to itself which commutes with the action of every element of G, okay? So eta is just giving a function, doesn't even have to be a bijection, just a function, eta dot from x to x that commutes with the action of each group element of each G and G, okay? And what I mean by that exactly is, so let's see, G dot eta dot of some element x is equal to eta dot of g dot x. And it's important to be careful here, so this dot is, well, which action is it? It's the action defined by capital G, right? So this is, ooh, those are really bad names, because the G is what I call my group, right? Okay, well, let's call the group something else. Let's call it capital gamma, okay? Okay, these are gamma sets. Gamma sets, and that's also a gamma. Anything else? Okay, we're good. Okay, and that's also a gamma. All right. So this is the action afforded by that functor, okay, capital G, whereas this dot in here is the action afforded by capital F. Okay, that's what's going on here. Okay, so you can play the same kind of game with representations, okay? And now if you think about it, everything is pretty much the same, except now a morphism of your target category is not going to be a function from this set to itself. It's going to be a linear map from the vector space to itself, okay? So in that case, you get what's called a morphism of representations. And that's what I was referring to when I was talking about writing down a list of all the isomorphism classes of irreducible representations, because you have this concept of when two representations of a group are equivalent. And it's just an isomorphism. It's really just a natural transformation from one representation to the other, which is invertible as a natural transformation, okay? So this is a lot of machinery, but it's actually very useful. So now I'll do the linear algebra example. So this is the example of this natural double duality isomorphism, okay? So if V is a vector space, we have this map, this linear map, and I'll write it as this fancy E, and it goes from V to V star star. And anybody who's taken linear algebra can tell me what this map does. It takes a vector over here, and it sends it to the thing that evaluates at V. So I'll write it as ev sub V, okay? Where I need this thing, ev sub V, to be an element of V star star, right? But what's an element of V star star? It's a linear functional on the dual, okay? So ev V needs to be a linear map, okay, by the definition of the dual space, needs to be a linear map from the dual space into the underlying field, okay? And how is f sub V defined? Well, you take a linear functional on V, and you evaluate it at that vector, and that gives you a scalar, right? So this is how you define this kind of embedding of V into its double dual. You can show that this is injective, okay? And in finite dimensions, it's also surjective, so it's actually an isomorphism in surjective infinite dimensions. For infinite dimensional vector spaces, it will fail to be surjective. So I guess to state this formally, what I want to do is I want to, so now let C be the category of vector spaces over my field K that are finite dimensional, okay? Consider two functors. Okay, the first one is the identity, so this goes from C to C. Takes every vector space, sends it to itself, takes every linear map, sends it to itself. The second one, I'll do it like this. So what it does is it eats a vector space, and it produces a double dual. Okay, so this is just, V goes to V, and this one is, if I have a V, and this guy sends it to V star star, which of course is this space. Right? Okay, and what does it do to, so I won't write the behavior on morphisms for this functor, but for the double dual one, I'll do it. if you have a linear map T from between two vector spaces, this guy, well, when you dualize once, you get a map from W star to V star. Dualize again, now it's going the right way. So it goes from V double star, you have this T double star, he goes to W star, double star. Okay, so when people say that a vector space is naturally isomorphic to its double dual, they really mean is that then these maps, okay, so let me write these, let me relabel these as eta sub v, okay? So what these are, they're going to be the components of a natural transformation from the identity functor to the double dual functor. Okay, so then these maps, eta sub v, from v to v star star, if you take the family of all of them, they form a natural transformation from id to, so they're a natural transformation between these two functors. Now, a natural transformation, you can find an inverse to a natural transformation if and only if all of the eta sub, all the components of the natural transformation are actually isomorphisms in the target category. Okay, so since eta sub v are all isomorphisms of vector spaces, there exists a natural transformation eta inverse going the other way. So going from the double dual to the identity functor. So this is identity on C, right? Which was my category of finite dimensional vector spaces. Okay, so I can find an inverse to this. So we call this eta a natural isomorphism. Okay, so that's the technical framework you need to build up to make sense of what people mean when they say this word in math. Okay, so now that all that's out of the way, I've been here for what?
An hour and 2 minutes.
Okay, so I have a bit more time. So I can try to talk about some constructions that come up in category theory. So I said that it was kind of a framework for organizing the way you think about things. If you do a lot of different types of math, so for example algebra, whether you're dealing with groups or rings or modules or whatever, you always have the same kind of patterns that tend to occur over and over. So given two algebraic structures, you want to be able to put them together in some way. You want to be able to take direct sums and products and things like that. So, and they all seem to turn out to be the same thing. So as a set, the product of two rings, the product of two groups, of two vector spaces, it's always just the Cartesian product of the underlying sets, right? So what I want to do now is kind of give a conceptual framework that will unify all of these patterns that tend to show up, these seemingly disparate branches of mathematics into one concept. Okay, so let's start with the simplest example of products. Okay, so just to keep it simple, if A and B are sets, we can form their Cartesian product. So it's A cross B, it's a set of all ordered pairs. A, B, where A is in A, and B is in B, right? So now I'm going to show you a property of this thing which characterizes it up to a bijection. So the crucial property of A cross B is as follows. We have projection maps onto each factor. Okay, so we have projection maps pi A from A cross B down to A, and pi B from A cross B to B. Okay, and the crucial property of the product is that these projection maps are somehow terminal among all cones that you can draw over this base that has A and B as its vertices. So this is where the pretty pictures really start to begin. So here's A, here's B. Up here we have the Cartesian product of A and B. We have these maps. Actually, I should probably draw this in a color because it's so special. So let me think about A cross B. I got my projection maps onto each factor. Okay. Now, the crucial property of the Cartesian product of two sets is that whenever I have some other set, C, okay, and it comes equipped with these arms that reach down to A and B, so call these F and G, whenever I have this situation occurring, so if you just think about what this is doing, you've got this other set C, and you've got this function that's sending it into A, and it's sending it into B, right? If I put those two pieces of information together, I get, what do I get? There's a unique function that I can define from C to the Cartesian product such that all the triangles involved in this diagram are commutative. Okay, so how do I define this map H? Or I might call it F cross G, right? So call that H. How do I define H? Well, H of anything in C, what's it going to be? I need a pair. Well, just take F of C and G of C. Okay, if I define the function H this way, then you can see that all these triangles do commute. If you take a C here, this gets sent to this pair. And then if I project onto the A factor, I just get F of C, right? But that's exactly F of C. And same thing for this one, right? So this is what I meant when I said it was terminal. You can see that if you give me any other cone above this kind of, so you really want to think of A and B as living in like down here on some plane, right? And now these are kind of like they're above the plane, right? For every cone above this diagram down here, it will factor uniquely through this terminal cone. Okay. Now, it turns out that every single product, pretty much every single product that people talk about in mathematics, is characterized by this kind of universality. Okay, so let me write this down. For every, this is what people call a universal property. For every set C and functions F from C to A, G from C to B, there is a unique function H from C to this product such that the commutativity of these triangles merely reads, well, pi A circle H equals F, pi B circle H equals G, okay? So this is the universal property of the product. Now, if you give me any category, we were just talking about sets here, but if you give me any category, I can say, okay, well, let's say that I have two objects, A and B, in that category. Is there an object, which I might denote by A cross B suggestively, in that category, that satisfies this universal property when I replace all these sets with objects and all these arrows with morphisms in that category? And this isn't true for an arbitrary category, but for almost all the examples I listed, it is true. So they all admit products. So for rings, groups, vector spaces, topological spaces, these are all just products of groups, rings, vector spaces, and topological spaces. Okay, so they're all just characterized by this. Okay, so the other thing you see a lot in algebra is the concept of a kernel. So if you have groups and you have a homomorphism from one group to the other, you can look at all the stuff that gets sent to zero. Okay, same thing with linear maps, right? Because linear vector spaces are really just abelian groups with some kind of action of a field on them, right? So you can really just forget about You know, so if I have a linear map, I can always look at the set of all vectors that get sent to 0. It's the kernel, or the null space of the linear map, right? So, slightly more generally, let's talk about the concept of equalizer. So here's the setup. If I have A and B are objects of C, and I have functions, so let me say I've got f from A to B and g from A to B. So I'm going to draw the picture now. Looks like this. You got this pair of parallel arrows, okay? What I want to do is find some other thing here, question mark, okay? Some other object with a morphism into A, such that these composites are equal, okay? So the case you want to keep in mind is when f is, say, a linear transformation and g is just the 0 map from A to B, right? In that case, this thing is the kernel if it's terminal among all such objects, okay? So what do I mean by that? The kernel, K, is an object with a morphism into A. So let me go back to the case of equalizers. So these are just general functions, but really the motivating example is a kernel, okay, when g equals 0. So an equalizer is an object E together with some map U from E to A, such that f circle U equals G circle U, and such that whenever I have some other object question mark with a V like this, such that, you know, doing V then doing F equals doing V then doing G. So whenever that happens, I get a unique morphism. So this thing is really the universal thing. So E is the universal guy. And this one is just some arbitrary thing. Whenever I have this condition happening, I want there to exist a unique, I don't know what to call it, W? Like that. Such that all this stuff commutes. Okay? So this is the general concept of an equalizer. And a kernel is a special case of this. So a kernel is a special case when this is 0. Okay, now you can't always make sense of a 0 map in an arbitrary category, but when you're in the category of, say, groups or vector spaces, you can, there's a thing, like the trivial group or the trivial vector space, and to get a 0 map from A to B, well, you have a map like this, you have a map like this, so you just compose them, and you call this map 0, okay? So my point is that in those categories, there is an object which is both initial and terminal, okay? So the trivial group, if you give me any group G, there's a unique group homomorphism from it into G, right? There's also a unique one the other way. So it acts as both an initial and terminal object. Okay, so the kernel is a special case when we just take this map to be 0. So if you just think about what this is saying, it says that, okay, say A and B are groups, and F is a group homomorphism, right? And the kernel is some other group equipped with a group homomorphism into the domain of your F, okay? Such that if I do, if I take an element here, send it into A, and then follow F, I get 0, because this is a 0 map, right? So because F circle U equals G circle U, it has to be 0. And it's such that if I have any other group sitting kind of, imagine it as sitting inside A, such that F of all of its elements are 0, then there has to be a map like this. So what this is really saying is like, the kernel is the largest subgroup of A that is killed by F. All of whose elements is killed by F. If you give me any other subgroup, all of whose elements are killed by F, it must kind of be a subgroup of this kernel, right? So that's the idea there. And then, so the thing about category theory is that it's all about these arrows and all about these pictures. So every time I write down one of these universal properties, I can just flip all the arrows in all the pictures, and then I get some concept that's dual to the one I started with. So if you flip everything over here, right, So here I was talking about products, you have these projection maps, right? So think about what would happen if now I had maps coming from a set into something here, coming from B into something here. What would this thing here be? It's going to be the disjoint union of A and B, right? Because the disjoint union comes equipped with an inclusion of A into it and an inclusion of B into it, such that whenever you have some other set C and functions from A to C and B to C respectively, I get a function from the disjoint union to C. So the disjoint union, instead of being terminal now, is initial among all cones coming up out of this plane instead of going down into this plane, right? So there's this concept of duality. You can just dualize all of these concepts, and you get other ones. So just for fun, let's just so products of vector spaces, right? I talked about products over two families of two objects, but you can do it over arbitrary families, right? So, for example, I can take the product over all, so let's say I have infinitely many vector spaces that are all just copies of the real numbers, okay? Then I get this object. And I can also take the direct sum of vector spaces, okay? And that one is denoted like this. Okay, now if you look at the properties, this thing is it's got these projection maps, right? You got countably infinitely many copies of R here, and you have projections from this object onto every one of them. So what this turns out to be is the set of all sequences, real valued sequences. Okay? But this thing, surprisingly enough, is not the same as this. Even though, for finite families, the direct sum and the product agree, for infinite families, life is not so easy. So what these are they're also real value sequences, such that if you look far enough down the sequence, it all just dies. It all just becomes zeros from that point out, right? So such that you can find some n with AI equals 0 for all I greater than n. Okay, so these are the finitely supported real valued sequences. Okay, so this thing has a bunch of inclusions, right? You have all these R's down here, and they all have these maps coming in to the direct sum. And it's such that if you give me any other vector space up here, and you give me a bunch of arrows into there, then there's a map from this into that thing, right? So it's initial, whereas this is terminal among cones that come down, right? So I want to make this precise because there are a lot of objects that tend to crop up, which arise by taking these limits of cones. Okay, so now I'm going to talk about diagrams. So if you remember from the beginning, I mentioned that if you give me any set, right, I can form a category whose objects are just the elements of that set, and the only morphisms are just the identities that I have to have, right? The ones that are forced by the definition of a category. It's a very silly category, but it turns out that it'll be useful. So a diagram of shape J. Okay, so J is a category. A diagram of shape J in some other category, in this C, is nothing more than a functor from J to C. Okay, so usually think of J as some kind of indexing category. So, for example, if J is the discrete category on a two-element set, so you can easily draw this picture of this thing. It's got two dots, and they both have loops on them, right? That's J. Then a diagram of shape J. What is it? A diagram of shape J in C is just a pair of objects of C, not necessarily distinct. Right? Because if you look at the definition of a functor, the definition of a functor tells you that each object here has to go to some object of C, and each morphism here has to go to some morphism on those images. But identity arrows have to get sent to identity arrows, so there's no information there. The only data it's giving you is a pair of objects in C, not necessarily distinct, okay? So what I want to talk about now is generalizing the situation to the case where in this plane here, in this blue plane, we may not have a situation that looks this simple. It may not just be two objects. It may be this big system of objects connected with all these morphisms between them. And then I want to talk about cones over that system. And then I'm going to talk about terminal cones. And those will be called limits of those diagrams. Okay. So what I'm getting at is that a product will be a limit of a discrete diagram. That's the punchline. Okay, so, and a coproduct is going to be a co-limit of a discrete diagram, yeah. But again, like I said, you could take a discrete diagram where, you take this one, but instead of just two elements, it might have one element for every real number or something, right? Like you could have this big family of objects in your category, and you could talk about their product as well. Just like here I had an infinite collection of vector spaces, right? So I could take J to be the discrete category on the set of natural numbers, and then make, the diagram would just be the functor that takes every natural number to this vector space, one-dimensional vector space over the reals, right? So, okay. So things are going to get even more abstract from this point on. So now I have this concept of a diagram, and I want to define limits of diagrams. Now this is all still very mainstream category theory. This is really like the first two chapters of any book on category theory. So it may seem like I'm doing some kind of really obscure fringe stuff here, but it's just the basics. So, right, so I got my diagrams. Now I want to, so how am I going to do this? So say say D is a diagram of shape J. Okay, this is really redundant. It's already told you the signature. Okay, so it's a functor from this indexing category to C. Say I have a diagram of shape J and C. I define a new category. As follows. And this is something I think is really cool, okay? It shows that we can make up categories whose objects are basically, as weird as we like. So I take this diagram and I'm going to make a category whose objects are cones above D. That is, they are pairs. So you've got a vertex. In other words, you've got an object of C. So call it V for vertex. And then you've got a family of like these arms that come and branch down to all these elements, to all these points in your diagram. So how should I say this? So it's a family V, and then I've got this collection phi sub j as j runs over the objects of j. Okay, so you got V up here, and then you got all these phi sub i's. Okay, and here you have di, dj, dk. So remember that J doesn't have to be a discrete category anymore. It could be a category that looks like this. Okay, so J could look like, you could have a dot, identity on this guy, and maybe you have an arrow like this, right? So it could look like that, in which case the picture that it paints in C is going to have two things and an arrow between them, right? So it's a pair of a vertex with all these arms, such that basically all the triangles you could possibly imagine commute. So whenever J to J prime is a morphism of the indexing category, this triangle commutes. So I have d of j, so let me call this thing, maybe I'll just leave it unlabeled. So it's clear that what I mean here is I take the image under my functor d of this morphism between these two objects, right? And then I have v up here, and then he has his arms coming down, phi j prime, okay? I want all these to commute. Every single one of these triangles needs to commute. So, i.e., oh, I really need to label this now. Call it f. This is d of f. So what I need is d of f composed with phi j equals phi j prime. Okay? Okay. So how can I phrase this more succinctly? We've already developed a lot of machinery, so I should be able to say this very, very concisely. And actually, it turns out that I can. Okay? So before I do that, here's another example of a category. Okay, so C and D are categories. The functors f from C to D are objects of another category of what's called the functor category. Okay, and it's written with these square brackets CD. So this thing is a new category whose objects are functors f from C to D, and whose morphisms, of course, are natural transformations. Okay, these morphisms are given by our natural transformations. Okay. Okay. So then, what do I mean by a cone? This is a very kind of the definition I gave over there is kind of cumbersome, right? Oh, so these are the objects of the category. Okay, they're these cones above the diagram. But the morphisms of the category, of course, they're going to be arrows between the vertices of the cones that make everything work, right? So how can I phrase this in a very concise manner? So alternatively, a cone over D is just, well, what is it? So what it is it should be, so I gotta get the vertex somehow, right? It's just an object C of it's an object C of C, yeah, of course, together with a natural transformation and it's going to be eta, and I want this thing to take a functor that I'll denote like delta C. Okay, so delta C is going to be the constant functor C, and then it has to go to my diagram. Okay, so where this thing delta C, this thing is going to be, you know, a functor from J into C, is defined by sending all the objects of J to this fixed object C. Okay, so it's like a constant functor. I've got this J that's like an indexing category, and the way I'm forming this delta C is I'm just sending all the stuff in the indexing category to the same object of C. Okay, and all the arrows in the indexing category, I just send them all to the identity on C. Okay, so and all morphisms of J to the identity morphism on this object C. Okay, so this is a constant functor at C. Okay. Okay, so what is this saying? A cone over D, what it is it's an object C of C together with a natural transformation from this to this, right? What does that mean? what does it mean to give a natural transformation from this to this? Well, these things are both functors from J to this category, C, right? So a natural transformation amounts to giving me, for each thing in my indexing category J, it's going to give me a morphism of elements in C. Okay, so let's just unwrap the definition. So if you think about it, this amounts to giving for all objects in your indexing category, objects J of J, what do you get? You get a component, right? So, and it's a morphism of C. And what does it do? It takes this fixed object, which is delta C of J, okay, because delta C is a constant functor, it takes this object C of C, and it sends it where? It sends it to D of J. So if you look at this picture, you can see how this is kind of the same thing, because you're taking an object of the category and you're getting a natural transformation from the constant functor down to your diagram, which is exactly this, okay? So encoded in this one thing, in this one natural transformation, are all these arms, all these branches that are reaching down, touching your diagram, okay? And what about this commutativity condition that I said? So whenever I draw one of these triangles, I need it to commute. Well, of course, that just comes from the fact that this eta is a natural transformation. Okay, it's a natural transformation from functors from J to C, which means such that whenever f from little j to j prime is a morphism of the indexing category, morphism of J, the triangle, which I get by drawing, well, what is it? I got this thing, I got this thing, I got delta C of f, and then over here I have d of j prime, d of f, okay, and it's giving me these components, so like this, right? But notice that this is the identity map, right? So these things are both, by definition of the constant functor, they're both just C. Okay? And this is just the identity of C. So in fact, this isn't a square. It's a triangle. Okay? So that's exactly the constraint that I gave earlier in this less concise framework. Okay? So it really does make sense to define a cone as an object of C together with a natural transformation from the constant functor at that object down to your diagram. Okay. So, and then as I said before, we can talk about a morphism of cones. Okay. So what a morphism of cones is going to be is it's just going to be a morphism. So say I have say C and C prime are cones over D. Then a morphism from C to C prime is in the category of cones is just a morphism. So maybe I should say like CC and CC prime. Okay, these are two cones, and their vertices are C and C prime respectively. Okay, then a morphism like this in the category of cones is just a morphism like this in C, such that everything works. Okay, so such that all the triangles commute that you would draw. Okay, so now I can finally define the very important concept of a limit. So a limit of a diagram D of shape J in this category C is just a terminal object in the category of cones over D. Okay. So again, if you just think back to the case of products, then your diagram is something of shape J, where J is a discrete two-object category, okay? And your D is just giving you these two objects of your category. And then when you take a limit, when you look at the category of these cones, and you take the last one, so to speak, the one that everything else factors through, okay? So a limit of a discrete diagram, that is a diagram of shape J where J is a discrete category, is simply a product. And similarly, when you take a colimit of a discrete diagram, you get a coproduct. Okay. So it's now 9, so an hour and a half now?
Hour and 36.
Okay, so I'll just quickly mention a few other things that are also pretty important, but this is getting kind of long by now. So let me talk about adjunctions. So what do I want to say by an injunction? Start with an example. If B is a basis for a vector space V, then to give a linear map, T from V to W, okay, W is some other vector space, suffices to give the behavior on B. Behavior on B, on the basis. Once you know where the basis goes, that fully extends to a linear map on the whole vector space, right? So we can write this in this kind of clever and suggestive way. The collection of all functions from this set B to the underlying set of any vector space W, okay, is in natural bijection with the collection of linear maps, so Hom vect, from the vector space whose basis is B, okay, so we'll write that as f of B for free vector space on B to W, okay? So the idea is just that if you give me any set B, I can form this vector space, which I denote f of B, that is just kind of like the span of the elements in B, okay? I just take all the formal linear combinations. And that gives me a vector space whose basis is basically identified with the set B itself. And then, this is just saying that every function from B into W, like I mentioned before, uniquely determines a linear map from that free vector space into W. And conversely, given any linear map, you can restrict it just to B, and you get one of these functions, right? But it's much stronger than that. So, since I've already talked about natural isomorphism, what I really mean by this, so to be completely precise, and this is somehow natural in B and W. Okay, so here's the definition. If F from C to D and G from D to C are functors, we call them, we say F is left adjoint to G. Similarly, G is right adjoint to F. If the functors, so the first one is going to be this. So if I take, so here, my F was going from set to vect. Okay, C was set, D was vect. And then G is the thing that takes a vector space and forgets it as a vector space, right? Just views it as a set. Okay, so we say F is left adjoint to G if these functors. So I want Hom C here, and then C, G, so let me write dashes here, okay? If this, and where does this go? Well, it's waiting for an object of C, right? And it's also waiting for an object of D. And then it gives me a set. So that's the signature of this functor. And what's the other one? Well, now I take in D, but now I do this, right? So now I have f of dash, dash. And now this thing is waiting again for an object of C, object of D, and produces a set. Okay? So I have this pair of functors, and I can talk about whether they're naturally isomorphic. And that is precisely the concept of an adjunction. So I say f is left out into G. If these two functors, notice that they have the same codomain and domain categories, are naturally isomorphic. So I should mention, just like for sets, you can also take products of categories. Okay, so this thing is a category whose objects are pairs of one object from C, one object from D. Whenever you have a morphism between two pairs, it's just a pair of morphisms between the components, right? So you can take products of categories, it makes perfect sense. And whenever you have these two things are okay, so I guess I need C and D locally small, because otherwise, I'm pretty sure that I just made that assumption throughout this whole talk that I'm working with locally small things, but if I don't have that assumption, then I don't know that when I plug things in for these dashes, this thing I get is actually a set, okay? It could be like a proper class. So that's the concept of adjunction. So again, examples. So if C is set and D is vect, then I can take F to be the free vector space functor. It takes a set, sends it to the vector space that has that set as a basis, and G to be the so-called forgetful functor. So I forget that I am a vector space and just view myself as a set. Okay? You can easily figure out what these do on morphisms. I just told you what they do on the objects. Okay? So that's an example of an adjunction. A really nice other example of an adjunction, if you've say you've done some functional programming, you probably know about this concept of currying. So if you have a function of two arguments, you can view that thing as a function that waits for its first argument, and then it returns to you a function that's waiting for the other argument, which is also a single variable function, and then it will output a value, right? So another example of an adjunction is given by what's called currying. So what we have is, in the category of sets, we have Hom set between, forgive me, so the set of functions from A cross B to C is in natural bijection with the set of functions, I don't want to keep writing set, from A into this other object. Okay, notice this is also an object in the category of sets. Okay, so this is currying. If you give me a two variable function, takes one argument from A, other argument from B, returns something in C, I can view that as something that takes something from A, returns to me something that's waiting for something from B, and then returns something in C. Okay. So why is this an adjunction? Well, take C equals D equals set. Okay, and let's take F to be the functor that takes the product with B. Okay, so it's waiting for another set, and then it returns to you the product with B. Okay, and what's G? G is this functor, Hom set B dash. Okay, so if you take F and G to be here and you plug them in here, okay, then you see that it reads exactly this. Okay, I could put dashes everywhere in terms of the A and B and C, but you get the idea, right? Okay, so those are some adjunctions tend to come up all over the place as well. So there's many examples like this. You could take free group on a set, free vector space. You got currying. There's an adjunction between well actually, it's actually an equivalence of categories. So I should define that as well. So C and D are categories, okay? Say F, you have one that goes this way, one that goes this way, are functors. Then they constitute an equivalence of categories. So this is kind of the concept of an isomorphism between two categories. Okay, so an equivalence of categories. If, so your naive guess would be like, okay, well I want F circle G to be the identity functor on D, and I want G circle F to be the identity functor on C, right? But it turns out that that's way too strong. There are plenty of instances when you have kind of constructions that are mutually inverse, but they don't actually get you back to exactly what you started with. They get you back to something that's isomorphic to what you started with. So instead of requiring that they're actually strict inverses, I want this. So I want F circle G. That's a functor from D to C back to D, so it's just from D to D. This needs to be naturally isomorphic to the identity functor on D, okay? And G circle F needs to be naturally isomorphic to the identity functor on C. Okay, so this is an equivalence of categories. It's kind of a loosening of the concept of isomorphism. But it turns out this is way more useful than the concept of isomorphism. When you have two categories that are equivalent, it's kind of philosophically telling you that whether you study one category or you study the other, it's somehow the same thing, right? So what are examples of some equivalence of categories? Well, okay, well I won't write this down because this may be a little bit beyond people, but so if you take the category of affine varieties, okay, that thing is actually equivalent to the category of finitely generated reduced algebras over the base field. Okay, this is a thing from classical algebraic geometry. It tells you that if you want to understand a geometric object, namely an affine variety, it suffices to understand its ring of polynomial functions defined on that geometric object. Okay, and another example is from analysis. So if you have a topological space and it's compact, I can look at the continuous functions defined on that space, right? And since it's compact, so this is a ring, okay? The continuous functions on that space form a ring because you can add them pointwise and you can multiply them pointwise. And the identity is, of course, the function that's just one everywhere, right? And so that what it gives you is, it gives you a commutative ring with identity. But not only that, it actually gives you something from analysis, an object from analysis, which is called a commutative unital C-star algebra, okay? So by taking a topological space and sending it to a compact Hausdorff space, okay, special kind of topological space, you send it to its C-star algebra of continuous functions defined on that space. This is an equivalence of categories. Between locally compact Hausdorff spaces and compact Hausdorff spaces and commutative unital C-star algebras. Okay, and that's called Banach-Stone duality. So essentially, what it's telling you is that you can somehow do topology by doing analysis, and you can do analysis by doing topology. So actually, people looked at this and they're like, well, if the commutative unital C-star algebras correspond exactly to compact Hausdorff spaces, then what about the non-commutative unital C-star algebras? And then that kind of gave birth to the field of non-commutative geometry. So they use analytic techniques to do geometry on non-commutative spaces, which is very non-intuitive, but pretty cool. Okay. So the last thing I think I'll talk about is the Yoneda lemma. And I think I'm going to state this in a very sloppy version, just because I don't want to spend too much time on it. But what it tells you is that, okay, if C is a locally small category, okay, so this is really a corollary of the full Yoneda lemma, but it's very nice to know nonetheless. Then C can be embedded in a category of set-valued presheaves. So in the category, functor category, COP set. Okay, so what is this? This is the category of contravariant functors from C to set. Equivalently, the category of covariant functors from the opposite category of C to set. Okay, and how do I get this embedding? So define the map Y from C into this freaky functor category, this category of set value presheaves, as follows. So what I do is I take an X, an object X of C. Where do I send him? How do I get a contravariant functor from C to set? Well, I talked about Halm functors before, right? So I can just send him to this. Okay, so I take X and I send it to the thing that waits for an object of C and returns a set of all morphisms from that object to X. Okay, so this is called the Yoneda embedding. And what you can show, so I won't write anything more down about this, but what you can show is it is full. And in fact it's faithful. So it's fully faithful. Okay. So what I mean by full, okay, if you have a functor from one category to another, you can look at what it does on the morphism sets. Okay, so you can look at the induced maps. Okay, for every morphism of the domain category, it gives you a new morphism between the images in the codomain category. So you get these maps between the sets. If all of those maps are surjective, okay, so in other words, if you give me any morphism over here, I can actually hit it with something from the domain category by using this functor, then that's what full means, okay? And faithful just means it's injective. So in other words, it's not the case that if I have two distinct morphisms over here in my domain category, C, and I send them through this thing Y into this category of set value presheaves, that they will hit the same arrow. Okay, they won't be mapped to the same arrow there. So the induced maps on morphisms are both surjective and injective, which is what this fully faithful means. And yeah, so what this allows you to conclude is things like this. So if I look at the set of morphisms in C between X and Y, that's naturally isomorphic to the set of natural transformations, that is Halm COP set between Y, oh god, I don't want to call this Y, call this Z, okay, between, this needs to be Y of Z, Y of X. Okay, so, is that right? No, I don't think that's right. It's the other way around. Okay, so what I'm doing is I'm sending everything to a contravariant functor from C to set, which means that this embedding itself is going to be covariant, which means that it does not flip the directions of the arrows. Okay. There is also a contravariant Yoneda embedding where you take C into the functor category C set by putting the X over here instead. Okay, you take the other Halm functor, and it does similar things, but then you have a flip going on here. Okay. So the Yoneda lemma is really, really useful. You can use it in conjunction with knowledge about adjoints to prove many facts that people ask you to prove in, undergraduate algebra courses. They'll say, okay, we defined tensor products this week. Can you check for me that the tensor product is commutative and associative? And you're just like, do I have to do this? And then you kind of sit down and you bash it out, and it takes you like 2.5 pages, but you do it. Whereas if you know this stuff, you can just say, oh, well, wait a minute. I know that the tensor product functor is left adjoint to the Halm functor on R modules. So by using the adjunction, so I use currying in a sense, and then I invoke the Yoneda lemma, I can actually conclude like in 4 lines that the tensor product is associative, as opposed to the people who had to bash out 2 pages of calculations to get the same result. So yeah, it's very efficient, and this kind of stuff can save you from wasting your time doing things that follow only from the formal structure of what you're working with, rather than any of the substance of what it is. Okay, so that's the whole power behind all these methods. So the other thing I wanted to talk about, but I think I'll stop here, was monoidal structures. So basically, if you look at the definition of a monoid, right, it's a set equipped with an associative binary operation for which there is an identity element, and you can encode the axioms. You can encode associativity and identity in some diagrams with arrows. Okay, so in other words, you got m cross m here, m cross m there, m cross m there, and n here. It's like if you multiply the first two factors first and then you multiply the result, that's the same thing as having multiplied the last two factors and then multiplying the result, right? So you can encode all the axioms that monoids have to satisfy in a bunch of pictures, and then you take those pictures, you pick them up, and you drop them in other categories. So you move them from the category of sets over to the category of, say, vector spaces, and you realize that miraculously, the definition of an algebra over a field is really just the exact same thing as the definition of a monoid, except you replace all the sets with vector spaces, you replace all the functions with linear maps, and you replace all the Cartesian products with tensor products, and that's just what that is. So monoid objects are pretty cool, and then if you've done functional programming, you've probably heard of things called monads. So the thing is that the correct setting to talk about monoid objects is a category in which you have an additional structure. So you have some kind of bifunctor, okay, which acts like a tensor product or a Cartesian product. And you can talk about monoid objects relative to that monoidal structure, okay? So it turns out that if you have a category, you can look at all the endofunctors in the category. So functors that go from it to itself, okay, those form a category. And then it's actually a monoidal category under composition. Okay, so the composition of endofunctors behaves a lot like the tensor product of vector spaces. And then when you look at monoid objects relative to that monoidal structure, those are called monads. And these things are studied, by people who like Haskell and stuff like that. So yeah, I don't really have any more time to talk about that. So thank you.